Hello dear students and Assalamu alaikum. I hope you are fine and doing well. In the previous lecture we have defined the Fourier transforms, Fourier sine transform and Fourier cosine transform as well. And I have also uploaded a video lecture regarding the application of Fourier transforms in order to solve the initial and boundary value problems for second order partial differential equation. Today I will try to explain you more things about the Fourier transform and one more important problem or an example which is very necessary for you for the course of partial differential equations. For this problem we will try to solve this problem with the help of Fourier transform, but more importantly in this question there are a lot of new things which are very handful for you for the exercise problems in which there are second order partial differential equations and you have to solve them. So what is this problem? Actually this is an example which I gave to you that you should learn and understand, but I am going to explain you with each step such that you can easily understand. So let's just write the problem. So this is example in the book of Devnath, and it says that solve the partial differential equation which is given as ut is equal to k u xx, okay, and the domain is given as minus infinity is less than x less than infinity. So x belongs to the real line. The initial condition is given as u of x of 0 is a function f of x, okay. Here x is also between minus infinity to infinity, so just we should put there. And the boundary condition, on the boundary we have the limiting conditions are, so these are not boundary conditions, they are limiting conditions, that u of x t approaches to 0, okay, u of x t approaches to 0 as x mod tends to infinity, okay, tends to infinity. Yeah. So before going to start the solution formally, I will try to explain you why these conditions are necessary. So if you remember the previous lecture where we defined the Fourier transform, just I am going to the definition where, yes, so here we define the Fourier transform that f should be on the real line or on the complex plane. So we are discussing in our course the functions on real line, number one. So the function mean that the variable according to which you are trying to apply the Fourier transform, which is x, this should belong to the real line. But generally our function will be of two components. The component along which you are trying to apply the Fourier transform, the condition is that this should belong to the complete real line, okay, number one. Number two is that the function has to be the provided that this integral exists, but this condition, if you remember, I had explained to you, was taken care by the fact that function is absolutely integrable, okay. So this represents that the function is absolutely integrable and this is also piecewise continuous. So these are the two necessary conditions for the Fourier transform to exist. This thing is also written in the Devnath book in the following manner. So if you go back towards the definition of Fourier transform in the book, what it says, so there is a definition. It says that, or maybe you can find here, yes, Yes. Note that all functions may not have Fourier transform. I told you last time that you should read the lecture slides and the book as well. For example, the constant function which is not 0, sine x function, exponential or x squared do not have Fourier transform. Why? Only the functions that tend to 0 sufficiently fast as x mod tends to infinity, I mean to say rapidly decreasing to 0 functions have Fourier transform. So this was the necessary or sufficient condition for a function to have Fourier transform, and this actually will solve all of your confusions in the mind that which are the special functions that possess Fourier transform. This was the question which I gave to you last time as well. So only functions which are sufficiently fastly converging to 0 or decreasing to 0 will have Fourier transform as x tends to infinity or x tends to minus infinity. So now what will happen, and what do you mean by exist? Exist means, or to have Fourier transform, it means that you will have a complete answer of the Fourier transform as a fundamental function. Okay, like I will explain in the example what is the Fourier transform of e to power minus x or minus ax here. I also explained in the previous lecture an example where I calculated Fourier transform of e to power minus ax here. So the answer was in the form of an exponential. So the Fourier transform of a function gives you a function in the omega domain, but that function is well known function and fundamental function. This means that Fourier transform exists, but for constant function sine x, x square, Fourier transform does not exist, yet we try to approximate the answers. So I will tell you more that what is the Fourier transform of 2020 in that example as well, which I gave you in the last lecture. So concluding the remarks, this condition is why useful, because if a function is tending towards 0, this is the first indication that Fourier transform must exist. So this is the first indication which gives you the instinct that you should apply Fourier transform. So in that lecture I will also explain you why using Fourier transform, and when you will have to use Fourier cosine transform, when you will have to use, so when you will apply or use, you can write any word, apply or use Fourier transform. Okay, this is the first question which is a confusing for all students, that when you will apply the Fourier transform or when you will apply Fourier sine transform and cosine transform. In our lecture series I am only intending towards Fourier sine and cosine transform apart from general Fourier transform. So when you will apply Fourier transform, this question is produces too much confusion into the mind. So when you are having the condition that a function approaches to 0 as x mod tends to infinity, it is the indication that Fourier transform exists. Okay, which I have already given you the instinct from that remark. Number 1. Number 2 is that when you are having this type of condition, look back at the derivative property of Fourier transform. So in that lecture I gave you the exercise, just you have to read out the condition regarding the derivative as well. So Fourier transform of double derivative is actually minus omega square and Fourier transform of u. So number 1. Number 2 is that when x mod tends to infinity, u tends to 0. So this is the given condition. Derivative of Fourier transform of the derivative also exists, and going forwardly that if a function approaches to 0, its derivative is also approaches to 0, we conclude that Fourier transform of double derivative also exists, and we have the formula. So these two formulas are proved actually from the fact that your function approaches to 0 as x mod tends to infinity. Number 1. Number 2 is that this is also the sufficient condition for a function to have Fourier transform. So we had one remark: whenever the function is between minus infinity to infinity and this approaches to 0 as x mod tends to infinity, we conclude that the Fourier transform of that function also exists. So if you look back at the example, at each step, this example gives you a lot of information that how you can proceed for the solution of any problem. So that is why this example is very, very important. So I am explaining you step by step what is the solution for that example. So concluding the remarks, yes. So concluding our remarks and moving forward, the question was, yeah, there was a question. I think that was, yes, this was a similar question. So now what we will do, so what we will do, we should apply the Fourier transform to both sides. Okay, number one. So whenever, this is the hint. Okay, so I am giving you the hint in the star commas, that whenever a function is between minus infinity to infinity, so I am writing that minus infinity to infinity, and also the function tends to 0 as x mod tends to infinity, or x approaches to infinity or minus infinity, both conditions are similar, then you should apply. Okay, then it is suitable to apply. Okay, we should write there, it is feasible or suitable to use Fourier transform. Okay, so this is the first instinct, that when you should use Fourier transform. Okay, so applying Fourier transform, Fourier transform to both sides of equation 1. What is equation 1? This is the main equation, so name that equation 1. Okay, so after applying the Fourier transform, this is the first step, that you should observe which transformation is suitable. So I have observed and explained you that which transformation is more suitable for you. I will also tell you when you should use the Fourier sine and or cosine transform. So this is the main step. Okay, yeah. Now apply. Okay, when you apply Fourier transform, what will happen? Just write formally as we had done previously. You should write capital F and here the brackets. Okay, so when you apply Fourier transform to both sides, what will happen? Look, on the left hand side you are having the derivative. Okay, I use one more step for you, implies that. So instead of this you should write the symbolic notation, partial u over partial t. Okay, and on the right hand side we use the formula. Okay, f k is the constant, it will be outside of the Fourier transform, and here you will write the double derivative. Okay, in the next step, if you remember the lecture, the points, that if you are having the derivative with respect to time, okay, as we are having there, and u is the function of two variables. Okay, u is the function of two variables. here also that derivative is also the function of two variables. Okay. So with respect to x you are applying Fourier transform, I should write here with respect to x. With respect to x you are having applying Fourier transform. So with respect to t derivative are optional, that you can take first the Fourier transform and then you can take the derivative, because x and t are independent. Remember that if x and t are not independent and they depend upon each other, then you cannot do that. So it is your choice that you should take derivative outside. Okay, the derivative outside, and you should take Fourier transform first. You can do that because x and t does not depend upon each other. So it is optional when you use the derivative and when you apply the Fourier transform, because Fourier transform by definition is an integral. Okay, and with respect to x we are having integral, and with respect to t we are having derivative. So it is your choice whenever you should use the Fourier transform. Now we are applying Fourier transform first and the derivative we are taking after that. Okay, on the right hand side k will be a constant, so it will be as it is, and the Fourier transform of the double derivative will be what? That will be, if you remember, minus omega square. Okay, this was minus omega was the transform parameter. Okay, if you want to write separately you can write that, and Fourier transform of u. Okay, Fourier transform of u. So this is the final answer. Implies that in the next step you can write that on the left hand side what is the symbolic representation of Fourier transform. So if you remember, we have written that the function will be similar, but instead of x you will have omega, because x, with respect to x you are applying the Fourier transform. With respect to so what will be u? U will become u like sinusoidal, because in the Fourier transform you have the kernel e to power minus iota omega x. This is what? This is actually sine and cosine combination. So we symbolically write the Fourier transform as u tilde. Okay. On the right hand side, what? Okay, we have also derivative. So we are having also the derivative. So when you you apply the Fourier transform on the right hand side, you will get minus k omega square. Okay, minus k omega square, and the Fourier transform of u, symbolic representation is this. So this is the first step, that you should apply Fourier transform. In the next step, which is also important, that you should eliminate, or you should find the expression of u tilde. Okay, so in that step what we will do? In that step we should try to find the expression for u tilde. This is the one, or you can also apply another transform, which is Laplace transform, because with respect to t derivatives are also there. What transformation do? It actually eliminates the derivatives and the partial differential equation is easy to solve. We know that we have the initial condition with respect to t, okay, for u. So it is your choice that you are applying Fourier transform, or and you are not applying Laplace transform or applying Laplace transform. So in the example, Laplace transform with respect to t is not applied. Okay, this was the example in the Devnath book. I am solving this example. I am saying that in that example the Laplace transform with respect to time is not applied. Okay, instead this ordinary differential equation, it becomes ordinary differential equation, and this has been solved using e to power mt type of solution. So but I am applying Laplace transform with respect to t just to have a different version of the solution. So applying Laplace transform with respect to with respect to time, okay, variable t. So when you apply the Laplace transform with respect to time, what you will get, look, when we have with respect to x the derivatives, we have already applied one transformation which have killed the derivatives, and now the equation becomes in that form, okay, this form. So applying Laplace transform in the second step, this is equation 2, applying Laplace transform to equation 2. But before that, I forgot one thing to tell you. Before that, you should also apply, okay, you have applied Fourier transform, okay, but you have not applied Fourier transform to this initial condition. This is the condition for t equal to 0, okay. So it is important that you should also apply Fourier transform to the conditions as well. One can ask that why should not we apply the Fourier transform to that condition? This condition is for x. So for x, we know that if this condition is valid, then the Fourier transform will exist, as I have written already. So this condition is for t. When you are applying Fourier transform, so this t condition will transform to another condition. So what will happen? Actually, the condition will remain similar, okay, the condition will remain similar, but what will happen if you apply Fourier transform to this, to both sides? What will happen? Okay, I should write there, what will happen? Fourier transform to both sides, okay. So implies that what will happen? The left hand side becomes u, instead of u will have u tilde, okay, u tilde, and instead of x we will have omega, and instead of t we will have 0, because we know that t is 0. And on the right hand side, what is the name of Fourier transform of f? It is just f tilde, because we don't know what is f. If f is e to power minus x, then we can apply the Fourier transform of e to power minus x, as we have already calculated in the previous lecture. But we don't know, if we don't know generally what is f, we can say that the Fourier transform is f tilde, and x will be replaced by omega. So this will be omega, and x will be replaced by omega, so this will be omega, okay. Your omega parameter will also be changed. Now this is important because you are applying now this is the transformed equation. This is known as transformed equation because this has been changed. So conditions will also be changed, because these conditions were initially for u. Now you are dealing with u tilde. So for u tilde, it is important that you should apply the Laplace transform to the condition as well. It is now what will happen? Applying the Laplace transform, I am telling you, it is not necessary to apply Laplace transform. When you don't apply Laplace transform, this will be an ordinary differential equation, because we have reached there. This is the ordinary differential equation if you take minus k omega square to the right hand side, and this can be solved using u is equal to e to power mt, as you had done in first semester of fifth semester, that y is equal to e to power mt, and you can put there easily, you can easily solve. But if you want to apply transformation, it is also possible. How can you apply? If you apply the Fourier Laplace transform to both sides, then what will happen? That what is the Laplace of derivative? You know that the Laplace of derivative is s y bar of u. So what do you mean by that bar? So Laplace transform of this, Laplace transform of this, okay. So we are applying Laplace transform initially is equal to minus k omega square, okay, the whole thing, and there is also Laplace transform, okay, as well. Now so what is the symbolic representation of Laplace transform? We will use that. So s there is also s Laplace of u minus s u of 0. Okay, so sorry, this was the total formula, minus u tilde of 0. This was the total formula for Laplace transform. So I forgot that, sorry. Now what is the symbolic representation? Symbolically, Laplace transform is used as bar. So what will u tilde becomes? Okay, step by step, what is u tilde become? U tilde will become u tilde bar. So when you put u tilde bar, okay, where is bar notation? Yes, there. So this will become u tilde bar, and on a minus the value of u tilde. So initially this was the value of u of x0. U of x0 is not the transform function. So transform function is u tilde, and u tilde of omega 0 is now f tilde. Okay, you will put there, and is equal to minus k omega square L Laplace transform of u tilde is, you know that symbolic representation is this. Okay, so now you will do the step which I was trying to explain you earlier, that you will eliminate u tilde. Now you will eliminate u tilde bar. You will find an expression of u tilde bar so that you can apply inverse transformations. So I am writing directly that what is u tilde. So not, this is not t, this is s, because t is changed to s. So this will become what? If you write directly, that will become f tilde, okay, divided by what? Divided by s plus k omega square. Okay, k omega square. Okay, k omega square. So this is the final answer of your transformed equation. This is the total transformed equation after applying both transformation. Look, initially we had the partial differential equation 1. In that partial differential equation we had, with respect to t derivative, this t derivatives and this in that PD you have already learned that how you can solve these in the previous semester using ordinary differential equations, that you can solve using Laplace transform. So that I have already applied it. Okay, one more thing, it is not customary that firstly you should apply Fourier transform and then you will apply Laplace transform. This is totally independent choice. You can also apply initially Laplace transform and then you can apply Fourier transform, but I have applied firstly Fourier transform and later the Laplace transform. Now the main step is the inverse transform. Okay, this is the main step, that you should apply inverse Fourier transforms. How you can apply? Okay, inverse Fourier transform. Okay, firstly inverse Fourier transform. This is also independent choice. You can also apply firstly inverse Laplace transform. Okay, I should do that, inverse Laplace transform. So remember that what Fourier transform does, this is only for you, I am just writing for your knowledge. A Laplace transform does, a Fourier transform does, x is changed to omega. Okay, what Laplace transform does, you remember that in that transformation t is changed to s. Okay, what inverse Laplace transform, to equation 3. Okay, name that equation number so that it will be easier for you to understand. So what inverse Laplace transform does, it actually gives back into the time domain the answer. So s is now changed to t. Okay, to equation 1, to equation 3. okay. And you know the firstly we should write symbolic representation, so that equation will be there, and on the left hand side we will have the Laplace inverse, okay. So shift Laplace inverse of the given function, and also we have on the right hand side the Laplace inverse of the given function. Now importantly, what is the Laplace transform of that function? This is a very easy symbolic representation, and in that form you can go back from u bar to u only. So you will get u of omega comma t, because s will become t, and there will be u, not u, this will be u tilde, okay. And on the right hand side, f tilde is not a function which includes s, so where there is s, you will apply the Fourier transform, okay. So Laplace transform. There is no s there, so it will be eliminated, and you can write Laplace inverse of the given function, which says that ratio 1 over, okay, 1 over s plus k omega square. Now what will be the answer? The answer will be f tilde omega, okay. And the Laplace inverse of u, it's very easy if you remember from ordinary differential equations, that Laplace transform is 1 of 1 over s plus a is e to power minus at. Maybe you remember e to power minus at, okay, minus at. What is a? A is k omega square, okay. Instead of a we are having k omega square, so the Laplace inverse will be minus a t. So this is the final form of Laplace inverse. If you look at the example, this is the solution which in the book have already calculated. They have used the Fourier transform parameter as this slanted k. I have used omega, and this k square was because of that coefficient. So, sorry, this k slanted was coefficient. I have used k here in the original equation, and instead of omega they have used something like small k, and I have used omega. So these are similar because that slanted k and k for Fourier transform was mixed up. So don't create the ambiguity. I have changed the Fourier transform to omega, and the k is for coefficient, that k, okay. Okay. So now the last step you should apply, because your task was find the u to solve the partial differential equation, but still you have u tilde. So the last step is apply inverse Fourier transform to the given equation, which is 4, okay. Now this is 4. So inverse Fourier transform, and what it will actually do, this will change omega to x, okay. It will give you back the variables, and we are applying to equation not 3 to equation 4, okay. When you apply Fourier transform to both sides, first write the symbolic representation. Always try to be at the very basic level, so because you will then not make mistakes. So just write the symbolic representation. On the right hand side also write the symbolic representation first, and then in the next step we will see what can we do for the inverse Fourier transform, okay. Now if you look carefully to the function on the left hand side, what will be the Fourier inverse? U tilde will become u, because tilde was for Fourier transform, and u tilde can be back to u, and omega will become x, and t was already there. On the right hand side you have to observe there, so how you can how you can calculate Fourier inverse transform. So if you remember the rules which I gave to you in the lecture slides, that I told you that you should also study the convolution theorem, just like for the Laplace transform. If you remember that when two functions, two Laplace transformed functions were multiplying, then the Laplace inverse was calculated by convolution theorem. So what we use, convolution theorem. So that is why I was saying that this example is very good choice to discuss, because in that example everything is coming. Convolution theorem for Fourier transform, not Laplace, because Laplace I was just trying to remember you inverse Fourier transform. What its theorems, and this theorem says that the Fourier transform of the two functions f of x and g of x, which are not multiplying, actually they are convoluted. Okay, they are convoluted. F of x star g of x, star means convolution, you remember from the previous semester, or if you don't remember you can also see Devnath book or the ZIL book which we discussed in the previous semester. So Fourier transform of the two functions which are convoluted is actually equal to Fourier transform of the first, okay, multiplied by Fourier transform of the second. Okay, so this was the initial convolution theorem. So how this can be helpful to find the inverse Fourier transform of the product. Look, what is the Fourier transform of f symbolically? So on the right hand side, on the left hand side we have the same thing, okay, and on the right hand side we have Fourier transform of f is known as f tilde. Okay, what is f tilde? It means that Fourier transform of f of x, and this is done by, sorry, not like that. Yes, maybe now it will be good. Okay, multiply by the other thing, Fourier transform of g. What is the symbolic representation? Instead of f you will have g. Okay, now if you apply inverse Fourier transform to both sides, what will be on the left hand side? On the left hand side you will have only the convolution, and this f will be taken to the right hand side. On the left hand side it is f, and on the right hand side it will be f inverse, not f. Okay, f inverse of the whole thing. Okay, so the total answer will be this. So you understand now that what will be the Fourier inverse of the product of two Fourier transformed things. So that will be actually Fourier inverse of f, which has the name f of x, Fourier inverse of g tilde, which has the name g of x, and the total will have the convolution. This will be the total answer of Fourier inverse. Now we will apply that methodology to the given equation. Okay, that idea will give you Fourier inverse of f tilde will be f, okay, and Fourier inverse of there will be star. Okay, Fourier inverse of this you don't know, first just write that. Okay, we don't know what is the Fourier inverse, we can write symbolically. Okay, Fourier inverse of that, and you should write that. Okay, now what will be the total answer? This is the complete answer of u of xt, but this thing has not been calculated. If you go back to the book, we have written that symbolically like that. This is the definition of convolution. Okay, you can write that. So I am writing here what this as convolution, because definition of convolution, name that. Okay, name this thing. Firstly, let this is equal to some, we don't know, g of x. I don't know what is g, but let's just suppose this is equal to g of x. Now what will be this equation becomes? This equation will become f of x star g of x. Okay, star g of x. What will be the convolution? The definition of convolution is 1 over square root 2 pi, 1 over square root 2 pi, okay, integral minus infinity to infinity, and there will be f of not x, this will be f of tau. Tau is a new variable. Okay, you can use any variable, but classically in the books tau is used. F of tau, g of x minus tau. If you remember from the previous semester, we had g of t minus tau, d tau, because there was only Laplace transform, d tau. So this is the definition of convolution. Okay, f of tau and g of x minus tau, d tau. Okay, now this in the book, if you want to see the step, you don't know what is the Fourier inverse of this, but actually I have explained you in the previous video lecture what is the Fourier inverse of e to power minus a omega square. It's not very difficult to calculate, and if you go to the example in the previous pages, just look at the example, the three examples which I said to you that you should understand. There, I think. Yes, look, the Fourier transform of e to power minus ax square is e to power minus omega square. We also are having omega square. Look, so it's very easy that we can calculate Fourier inverse of that kind of expression. But in the book, I am explaining you 2 more steps, because these are very handful and important, so that you can understand some knowledge about 2 more things. Now what we are doing, we are actually applying the convolution. Okay, and also we are applying the Fourier inverse of this type of thing. So if you remember, what is Fourier inverse of this thing? Okay, we know that by definition, we are going by definition, we know that what will be the Fourier inverse. If you remember the lecture slide, that Fourier inverse of any function was 1 over square root 2 pi, okay, minus infinity to infinity, f cap or f tilde and e to power iota omega x. This definition has been used there. Look there. Okay, f tilde is there, and e to power minus k square kt was the function originally. This was the function, and e to power iota kx was also there. E to power iota omega x, not kx. We are using omega. So concluding the remarks, I am going to apply the definition on Fourier inverse, because we don't know what is the Fourier inverse. So what will be the answer? The answer will be 1 over square root 2 pi integral minus infinity to infinity. Okay, instead of that we will have e to power minus k omega square. Okay, and e to power also minus plus iota omega x, because we don't know what is the Fourier inverse, but we are supposing that. Instead, if you remember, we know that what is the Fourier transform by the example A, which we did in the previous video lecture. So applying the Fourier inverse, this will be e to power iota omega x d omega, okay, d omega, sorry, d omega. Now this is the Fourier inverse, which is written in the book like that. And now we will apply the convolution on this thing, okay. Yeah, so this is actually equal to that. This is your exercise to prove that this is equal to this. How this has happened, okay, I explain you also this, that my claim is that this is equal to e to power, so my claim is that this is equal to 1 over, okay, this is equal to 1 over square root, okay, 1 over square root 2 omega t, okay, and there is what, e to power minus k square, e to power minus k square. Actually this k is used for the coefficient, so we should use here not omega, k, okay, and the other k which is not there, okay, because this was for omega becomes x square. So ultimate answer will be 1 over 2 kt exponential of minus x square, okay, minus x square over 4 divided by 4 kt. So this is the total answer of inverse Fourier transform. How? Again I am repeating, go to the part C or maybe part A, where we have found the Fourier transform of exponential, okay. This was the part A. The Fourier transform, in the previous video lecture I explained you the Fourier transform of, okay, Fourier transform of e to power minus ax square is equal to what? Is equal to 1 over square root 2a, 1 over square root 2a, square root 2a e to power minus k square divided by 4a. This is the general proof which I have explained you in the previous video lecture. And now apply this to the given Fourier inverse. So Fourier inverse of this will be what? Remember that Fourier on the right hand side will become Fourier inverse, okay, Fourier inverse, okay, Fourier inverse, and okay, Fourier inverse, we are taking f to the right hand side and you will be left with only exponential. Now Fourier inverse of this type of function is actually e to power minus k square over 4a. Look, if you remember, scalar is not the part of Fourier inverse or Fourier transform. So you can take 1 over square 2a to the right hand side, but if you take to the right hand side, that will become what? This will become not the ratio, it will become actually only the numerator, okay, this. So this is also equivalent form of the formula. Now we have in our data e to power minus k omega square t, and there we have minus k, okay, this is not k because the Fourier transform parameter we were using omega square, sorry. So now we are having because in that formula they use the Fourier transform parameter as k, we are using omega, so I have changed k to with omega, and that small k was the coefficient. Don't confuse yourself, this small k is the coefficient, that is why I used omega, because then both k's will be mixed up. Now implies that when you find the formula of your choice, you are having k omega square. Here is omega square only and minus also, but in the denominator we should have 4a. So how can you change this? You can change this like that. Okay, this is equal to e to power minus omega square divided by 4a. A should be that number such that the exponent or the power of e will be similar to k omega square. So what can you put there? You can put here 1 over 4 k, because then omega square divided by, okay, I should write that, okay, because the formula will be very easier for you now. Okay, yes, okay, omega square divided by 4a. A should be that number such that this exponent is similar to this. So if you see that 4 will be cancelled with this, the answer will be t over k, and k will be in the numerator because you have 2 times denominator. So the ultimate answer will be that kt, because then the kt will be in the numerator. So the ultimate answer will be kt omega square. But writing in that form is actually gives you the instinct to use the formula. Formula says that the Fourier inverse of this type of function of omega square is not easy to calculate. Instead, you have to make it omega square over 4a. So what is your 4a? A is 1 over 4 kt. So concluding the remarks, what will be the Fourier inverse? What will be the Fourier inverse of this thing? This will be equal to square root 2a, okay, square root 2a. So you prove that in your case a is what? A is 1 over 4 kt. Okay, so what will be the Fourier inverse? Square root 2a, square root 2a. A is 1 over 4 kt. There is multiply, okay, 1 over 4 kt, and on the multiplication you have e to power minus ax square. Instead of a you are having 1 over 4 kt. So I should write like that, because 4 kt and here will be exponent, okay, is equal to Fourier inverse of this, Fourier inverse of this, okay, no, Fourier inverse of this. So now implies that in the next step, so this was the hint, okay, I should write hint at that point, okay, this was the hint for you. Now in the next step implies that very easily Fourier inverse of this will be equal to what? Fourier inverse of this will be equal to 2 will be cancelled out, the answer will be 1 over square root 2 kt and e to power minus k x square over 4 kt. Okay, this will be your answer. This was the answer which I was saying to you that you should calculate by yourself, but okay, I have explained you now. So put that into the original solution. So total final answer will be your what? F of x convolution with the given function of Fourier inverse. So answer for Fourier inverse of the function is what? That function. Okay. Now this is your answer. Okay. Up till now, if you calculate, this is your final answer. Final answer. But moreover, in the final steps in the book, more things have been calculated. If you go back to the example in the book, there are 2 more steps which have solved and done in the example. What are these steps? They have also calculated the convolution. So this will be equal to what? Moreover, this is equal to convolution. So you should apply the definition of convolution. So definition of convolution says that this, okay, 1 over square root 2 pi f of tau. Instead of g, you know what is g now. This is the g. Okay, you should put that. Okay, g of f of tau, g of t minus tau. So how can you x minus tau? So how can you apply this? Instead of x square, you will have e to power not x square. You will have x minus tau square. Okay, because you are applying the convolution over 4kt will be similar because x will be changed to x minus tau. Okay, look, you will have x is changed to x minus tau, and f of x, instead of f of x you will have f of tau. So you put it f of tau there, and this was the coefficient, this will be similar, there is no x there, and e to power x square you will put x minus tau square. Okay, now rearranging the coefficients and these scalars, what you will get, u of x t will be equal to 1 over square root 2 will become 2, and you will have square root of what, pi k t. Okay or not? Or they have written 4, it's no problem, 4 pi k t, no problem, you can write also that. And integral minus infinity to infinity, minus infinity to infinity. Okay, and there the integrand is similar. Okay, f of tau. In the book the notation is not tau, the notation is f of xi. No problem, you can use also that, and e to power minus that thing d tau. Okay, d tau. So this is the next answer. Now why this answer is more important? Because look, this answer can be written in the following manner, that this is actually convolution of two things. What are the two things? So in the next step you can write it like that. Okay, so this is this u is actually equal to minus infinity to infinity, the integral will be similar, but that integral will be taken care by the following thing, f of tau, and there you should put g of x minus tau comma t. Okay, because g is function of x and t both. So what is g actually? This because we have changed the variables, g is actually equal to 1 over 4k this thing coefficient, and e to power this thing. Look in the book, so this is actually g. G is this is the replacement. Okay, not g. Okay, you can use capital G. This is of two variable, that is why this is very interesting, x and t. So x of with respect to x we have convolution, so that is why I have written x minus tau, and the thing is g of x minus tau comma time. So this function is known as green function. Okay, in the literature this is known as green function. Just to remember, this type of function is known as green function. Okay, this is also why important, this is the solution of diffusion equation. What do you mean by diffusion equation? Okay, in one dimension form. What is the diffusion equation? Okay, this is the solution of diffusion equation. What is diffusion equation? Partial C stands for concentration, by partial T is equal to what? D. The D is diffusivity constant in the literature, partial square C over partial x square. Okay, partial x square. This is known as diffusion equation in one dimension form, and this G is actually solution of that. Very interesting, because in the original equation, if you remember, there is no okay, there was also the similar equation. This is also similar to what I am saying, diffusion equation. The mathematical form of that equation, okay, I tell you, this equation in literature is known as heat equation. Okay, this equation in the literature is known as heat equation. Just for your knowledge, I am writing the heat equation. Okay, the diffusion equation, if you see mathematically, looks like similar to the heat equation. Yes, you are right. The mathematical form of diffusion equation is similar to the heat equation which you are seeing there. But the dynamics is different. So they are mathematically one-to-one correspondence, but dynamics of both phenomena are different. This is the equation which is used to capture the dynamics of heat in a rod in one dimension case, and this is used to study the particle concentration in a phenomena like diffusion phenomena, if you remember from basic classes. So the dynamics is the phenomena are different, but mathematically they are similar. Okay. Now what is the next step? In the next step, you will change the variables. If you change the variables like that we are having xi minus x whole square or x minus xi, no problem. You can replace xi minus x divided by 2 square root omega t to a new variable. So what will happen? You will get a new integral. Okay, so if we make change of variable, because these are basic notions, you should only know what is the new name. We make change of variables. Okay, you should make change of variables. So what will be that? You make variables of what? So you are making the change of variables of xi minus x. Okay, now instead of xi we are having tau minus x over 2 square root what kt square root okay, not k, maybe this k, yes k, okay, kt equal to new variable. Okay, new variable can be any other variable. They have used this symbol. I am using the same symbol just for your convenience. So this implies that if you take the differential, what will be the differential of that new variable? Okay, this variable has a name in the Greek letter, and this is known as zeta. Okay, so d zeta is equal to, in the both sides you should take the differential of d zeta with respect to this tau. Okay, so the answer will be d tau. Okay, d tau dx will be 0 because tau x does not depend upon tau, and this will also be behave like a scalar. So this will be the final answer of the change variable, and now the integral will become, so this will becomes, so you name that 5. So equation 5 becomes, okay, what will become? You will get actually u of x t equal to what new thing? Okay, you will get that f of this whole thing, okay, 1 over square root pi, because coefficient will be cancelled out, 1 over square root pi, because coefficients will be cancelled out, and instead of f you will have a new variable tau. Tau is what 2 xi multiplied by 2kt square root divided by x. So that is why I have there x plus xi 2kt square root. So this will be changed with x plus okay xi multiplied by 2kt square root, okay. And instead of the other thing, g was, you know that g what was that, okay. Instead of this you will have only exponential of what, e to power. So this whole thing is now replaced with xi. So only this will be minus or plus, maybe plus, no, minus zeta square. So this is another form of the solution by using the change of variable, simplest form. And this inform why this is important, because integral on the right hand side, if you have studied the statistics, this was used to observe the probability functions of some random variables, and this is known as Poisson integral. So Poisson distribution, if you remember, there was also something similar to that. So basically these integrals are very similar in the mathematical form, but they capture different dynamics or different structures. In this integral is known as Poisson integral, but this integral convergent for t positive and only for t positive. So after making some more changes, I am not going to explain, okay, I explain more changes. You will learn that what is the new form, okay. So when t approaches to 0 positive, you will have another form, and ultimately your integral will be into that new form. So I am leaving this step only for you. This is the last step that you should understand and do by yourself, that how after replacing so to say replacing the form that for t greater than 0 the solution will exist. So for t positive your solution will become like that, okay. So for t positive your solution will be like that, and if you change more variable as you have done previously, okay, you will get this form of solution. And by dividing the integral you will understand that you will have another unknown function which is known as error function, okay. So the solution is now transformed into an error function by using some changes. These are written on the page 452. So I am leaving this step for you to understand, because thoroughly I have explained you each step into that video lecture. And in the same manner you can also apply Fourier Sine transform. So why Fourier Sine transform is important? Look, just one line, so because we are concluding the lecture, that why Fourier Sine transform and cosine is important. Look, Fourier Sine transform is used to study the problems in semi-infinite regions, because in Fourier cosine transform or sine transform, what we do, we actually apply the transformations in the definition of 0 to infinity, okay. So this is the definition, 0 to infinity. So 0 to infinity is known as semi-infinite region, and definitions, you know what is the definition of Fourier sine and cosine, but when they will be used, this is more important. Actually both are used for semi-infinite region. 0 to infinity is used for sine, also 0 to infinity is used for cosine. But again the question, when you will use the cosine or sine, the answer is into the fact that what is the Fourier sine transform of the derivative, second derivative, and what is the Fourier cosine transform of the second derivative. So what is the Fourier sine transform of the second derivative is this. Look, in that transform, the formula, you are having f of 0, which means value of the function at 0. And in the cosine transform formula for double derivative, you are having the fact that you should know the function's derivative at x is equal to 0. So when in the problem you are given the condition with f of 0 is some value, maybe 2, maybe 3, maybe something else, you will use Fourier sine transform. And when in the problem you are having the value given, the derivatives value is given, you will ultimately use Fourier cosine transform. Something like that. Look, in the exercise, if I go back, just for your sake, you have to look at the domain. If domain is minus infinity to infinity, apply Fourier transform. But if domain is 0 to infinity, just like that, x greater than 0 means 0 to infinity, you can apply Fourier sine transform and you can apply Fourier cosine transform, which is suitable. This you have to select. How can you select? Okay, just look at if u at x equal to 0 is given or derivative of u at x equal to 0 is given with respect to x. With respect to x, derivative of u at x is equal to 0 is given? No. Only u at x is equal to 0 is given. So which formula is best suited? So which formula is best suited? This, because this formula has function value at x is equal to 0. This formula has function's derivative value with respect to x at x is equal to 0. So in question, for example, in question in the book 12, you will use Fourier sine transform. One more idea that what transformation is best suited to apply is this 18, maybe 18 I have solved already. Here the derivative of u with respect to x at x is equal to 0 is given and x was also between 0 to infinity. So what is the best suited formula? You should apply Fourier cosine transform, because in the cosine we are having double derivative formula as used as single derivative calculation. So with respect to x, you will apply, for the double derivative you will apply the Fourier cosine transform here. So this is the idea how you select which transformation is best suited, by just observing the double derivative formula. Like these I have double derivative formula, but if x is between minus infinity to infinity, you have only one choice, you should apply Fourier transform, that's it. But if it is between 0 to infinity, you have to select which unknown thing is given. If you are having double derivative, if you are having functions value at x is equal to 0, you should apply Fourier sine transform. If you are having single derivative of function at x equal to 0, you should apply Fourier cosine transform. So this is the idea that you should elaborate. Thank you very much for listening. This was a very long lecture, but was important just so that you can have some practice with Fourier transform problems. And few days I will also upload the assignment. Thank you very much for listening, and in the coming days you will get the questions for the practice in the assignment. Thank you.